intermolecular forces. Consider the model of a gas in which we see the molecules far apart from one another. Consider the model of the liquid in which the molecules are very close together. The molecules cannot be close together unless there is some attractive force holding them together. We call this intermolecular forces or intermolecular attractions. We can compare the intermolecular forces of liquids. I have 3 here. The names are on the board. I'll squirt some of each on the board. And we note they don't look the same. This one is almost gone. How can I compare those intermolecular forces with these? Much weaker. The distinction between these two that perhaps stands out is that the water forms beads. It beads on the surface of the blackboard. That's a result of the imbalance of the intermolecular forces. Within the body of a liquid, a molecule is surrounded, so there are attractive forces all around. At the surface, the molecule has attractions only into the body of the liquid, so there's an imbalance of forces. This is called surface tension. The result is the molecules at the surface tend to pull toward the body of the liquid, resulting in the beading effect that we see with the water. Another illustration of the surface tension. I'll fill the glass with water, completely full, and I ask the question, how many paper clips can I put in there before the water will overflow? 1, 5, 10? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 16, 19, 22, 23, 24, an awful lot it seems. You may note that the surface of the liquid is bowing so that the water is actually above the rim of the glass. It's the surface tension that holds those molecules together, pulling them toward the body of the liquid. A similar effect, I can take a paper clip, put a little flag on it, and float it on the surface of the water. Paper clips should sink, but because of the surface tension and the fact that I laid it gently on there, it does not break the surface tension, and so it floats. So then I ask, if the surface tension can hold the water in the liquid even above the rim when the glass is right side up, can it hold the water in the glass when the glass is upside down? So I'll fill the jar with water. Turn it over, and I see, yes, the water stays inside the jar. Really? You suspected something is amiss, and you are correct. You are being deceived somewhat. When I turn this and let the air get in behind the water runs out, and you can see the screen. The screen provides all these little openings, each of which has surface tension, and it is sufficient to support the water in the glass, along with the atmospheric pressure, to keep the water from running out. You saw when I tilted it, that when the air can get behind there, the water will no longer stay, but it will run out of the glass. Feel free to try these at home. One aspect of surface tension is that certain materials will interfere, will get in the way of those attractive forces between the molecules and thereby lessen the surface tension. Detergent is an example. Let me illustrate. I'll put some sulfur in the water. naturally on the water because the sulfur does not sink. It does not break the surface tension. If I put some detergent in there, it will interfere with those intermolecular forces and weaken the surface tension. Put a little detergent on my finger to see what effect that has. But to show that it's not my finger that has the effect, nothing happens when I put my finger in. When I put the detergent in, the surface tension is weakened and the sulfur cascades to the bottom. Surface tension is weaker, the sulfur can now break through. So when you see those little bugs walking on the water, don't put any detergent in the water, they'll sink. Thank you.